Are you taking a probability class and need some extra help with set theory? Or you're just trying to learn and looking for a complete video that will teach you all about it? Then look no farther. A complete video to learn set theory? Yep, that is right. Hi, my name is Oldrin Vasquez and I'm an industrial and systems engineer from Georgia Tech who is currently working as a full-time data scientist. I have designed this video so you can learn and understand set theory in a very easy and explanatory way. I know, I've been there too, statistics, probabilities, sounds kind of boring and complicated. Well, believe it or not, it's not that bad. You just need someone to explain it to you step by step. And hey, that person will be me. Today, we'll be covering set theory, starting with what probability is, set theory concepts and operations, Venn diagrams, cardinality, and functions. And if you want more videos like this, don't forget to subscribe and like this video. I'll also be reading all of your comments on what topic should I cover next. So, without further ado, let's jump into it. So, what is probability? Randomness and uncertainty exist in our daily lives. From waking up in the morning and choosing what you're going to do for breakfast, how long will you be waiting in the drive-thru line to get your food, is there a lot of traffic to your way home, to how late will you go to bed tonight? All of these that from now on we'll call them events that with enough data can be predicted using probability. So we describe probability as the mathematical framework that allows us to describe a random event in the world around us. Now, for example, we toss a fair coin. We don't know if the result of our experiment is heads or tails. We only know our probability of each event heads and tails is 50% for each one. There are two interpretations of probability: relative frequency and subjective personal belief. The first term is relative frequency. It means if we toss the coin a large number of times and we keep doing so, we'll get heads about half the time. The more we continue doing so, the closer our number will get to 1/2. And this is what we call the law of large numbers, which will be explained more in depth later in the course. The second interpretation is the subjective personal belief. For example, the weather. If we think it will rain today because it's cold, cloudy, windy, and humid, we're taking our own belief into consideration for the probability that it will rain today. And this can change from person to person. The beauty of probability theory is that it works regardless of what interpretation we choose. It is a solid framework to study random events, just like tossing the coin. Now that we have a basic understanding of what probability is, we'll move on to the focus of the video, which is set theory. Probability uses the language of sets, and we will see later that probability is defined and calculated by sets. So let's jump into what a set is. A set is a collection of items, which are the elements of the set. This can be anything: a car, a thought, a number, literally anything. We use a capital letter to denote a set. To define a set, we just have to list all the elements in curly brackets. For example, a set contains the numbers 1 and 2. To say that the number 1 belongs to the set A, we use the following symbol, and it is read as 1 belongs to A. If we're trying to say that an element doesn't belong to our set, we use the following symbol, and it is read as 3 doesn't belong to set A. In sets, the order doesn't really matter. Here's some examples for sets: the sets of natural numbers, the sets of real numbers, closed intervals on the real line, meaning all real numbers. For example, closed brackets on 3 and 4. Is the set of all real numbers x, such that x is greater or equal to 3 and less or equal than 4. Note that this set will include the numbers 3 and 4. Upper intervals on the real line. For example, the following one is the set of real numbers x, such that x is greater than -1 and less than 3. In this case, we're not taking into account the numbers -1 and 3. Same as this other one, is the set of the real numbers x, such that x is greater or equal to 1 and less than 2. In this case, we are taking into account the number 1, but we are excluding the number 2. We can also define a set by mathematically stating the properties. Set A is equal to X such that X satisfies some property. Note that the slash symbol is read as such that. So now we're going to provide a couple of examples. Let's say the set C is going to be equal to X such X that belongs to integers, where X is less than 10 but greater or equal than -4, close parentheses. Then, as a result, we get that set C is going to be equal to. Now, in order to solve this, we have to look at the integers. Integers that will be less than 10 and greater or equal than -4. So in this case, we are taking into account the -4. So we're going to start with -4, -3, -2, and so on until we reach 8, 9, and then we don't include the number 10. Let's do another example. Set Q is going to be equal to X squared such X belongs to the natural numbers. In order to solve this, then we need to know what are the natural numbers. Natural numbers is a set of all the numbers that start with 1, the positive counting numbers. So 1, 2, 3, 4, and so on until infinity. In order to find the set Q, we're going to take all the natural numbers, because X belongs to natural numbers. When X is equal 1, our result is X squared. So our first result here would be 1. When X is equal 2, our result is 2 squared, which is 4. And we continue. 3 would be 9, 16, and so on until we reach infinity. So that would be the solution for our set Q. We can also have a subset from a set. For example, if set A is a subset of set B, we use the symbol to indicate it is a subset. It means that all the elements from the subset A can be found in the subset B. In other words, B is a superset of the set A. A null set is an empty set with no elements and is represented by the following symbol. Now, the universal set is all the elements that exist in the context that we're studying. Consider this whole universe of our elements. In most books, this set is denoted as S, that in probability theory is called sample space. And just like our previous example with the coin, our sample space would be heads or tails, because these are all the possible outcomes that we can get when we toss the coin. So, Venn diagrams. Venn diagrams are useful in visualizing sets. In a Venn diagram, any set is graphed in a closed region. For example, this shows two sets, set A and B, where B is a subset of A and S stands for the universal set. Sets also have operations. The first one we're going to be looking at is union. Here we have B union A, that it's going to be equal to A union B. The union of these two sets, A and B, is a set that contains all the elements that are in A and B. For example, we have the set A1 that contains the following elements, A, B, and C. We have the set A2 that contains the elements C and H. And we have the set A3 that contains the elements A, D. And we're gonna do the union of these three sets. So the union for the number I of the subset I will be equal to set A1 union the set A2 union the set A3, which would be equal to. Here we also have to note that the elements do not repeat in a set. So we're going to combine these three sets, A1, A2, and A3, but we're only going to take unique elements. that will give us A, B, C. For A2, we already have C, so we're only going to include H. And with A3, we already had A, so we're only going to include the letter D. So the union of A1, A2, and A3 will be A, B, C, H, D. And we can similarly define the union of infinitely many sets as A1 union A2 union A3 union, and so on. That would be the union of I of set I. Now we're going to look at intersection. The intersection of two sets A and B is a set that contains all the elements that are in A and B. Here we're going to provide an example of intersection. We have the set A equal to the elements 1, 2. A, element 1, and element 2. We also have the set B that contains the elements 2 and 3. As you can see, what we have in common is the number 2. So A intersection B would be equal to the number 2. The next operation is complement. The complement of A is the set of all the elements that are in the universal set, but not in A. The next operator is difference or subtraction, and it is defined as follows. The set A minus the set B consists of elements that are in the set A, but not in the set B. Two sets A and B are mutually exclusive or disjoint if they don't have any shared elements. For example, the intersection is the empty set. Intersection between set A and set B will be null. So now we're going to explain two laws, the Morgan's law and the Distributive Law. The first one is the Morgan's law. The Morgan law says that for any sets A1, A2, A3 up to AN, we have that A1 union A2 union A3 up until union AN, the complement would be equal to the complement of A1 intersection of the complement of A2 intersection complement of A3, and so on up until the complement of AN. It also tells us the complement of the intersections now. It's going to be all the way up to AN. It's going to be the same thing as above, but the opposite. So it's going to be the complement of A1 union the complement of A2 union the complement of A3, and so on up until the union of the AN complement. This is the Morgan's law. So for the distributive law, it's going to tell us two things. The intersection of set A with the union of set B and C is going to be equal to, so we're going to distribute the set A with whatever is inside the parentheses, just like this. So we're going to get A intersection B union A intersection C. And we can also do it with, instead of intersection, we do union. So A union of the intersection between B and C, we're gonna do the exact same thing. A union B, but this time instead of union, we're gonna do intersection of A union C. And this is the distributive law. Now that we have explained all the different set operations, I know it might look like a little bit confusing, so let's clear some things out and give an example for all of them. Let's say that our universal set S is going to be equal to the numbers from 1 to 6. 1, 2, 3, 4, 5, and 6. We have our set A that is going to be equal to the numbers 1 and 2. Our set B that is going to be equal to the numbers 2, 4, and 5. And we have the set C that is going to be equal to the numbers 1, 5, and 6. We're going to find the following: A union B. In order to do this, we need to look at the sets A and B. And let's remember, we cannot have duplicates in our sets. So set A has 1 and 2, and set B has 2 that we already have in our set. So we're just going to include the rest, 4 and 5. Now let's do intersection. A intersection B. We need to look at what elements does the set A and the set B have in common. So when we look at it, we can only see that they have in common one element, which is the element 2. Now, A complement. By definition, this is all the elements that exist in the universal set, which in this case is S, that are not part of A. So we can see that the numbers 1 and 2 are part of set A, so we're not going to take that into account. So we're only going to include numbers 3, 4, 5, and 6. Now let's do the same thing, but for B. B complement would be, we're not going to take into account numbers 2, 4, and 5. So that would be 1, 3, and 6. Now we're going to check the Morgan's law by finding two things. A union B complement, that by the law it should be the same as A complement intersection with B complement. So we're going to solve this one first. For A union B, we already did it before, so that will be the set of 1, 2, 4, and 5. Let's not forget that we're doing the complement. So now the complement of this new set, which is A union B, would be, we're not taking into account 1, 2, 4, and 5. So the only ones that we have left would be 3 and 6. Now let's check it on the other side. We need to do A complement. A complement from the previous example is 3, 4, 5, and 6. Intersection with B complement. B complement was 1, 3, and 6. The intersection between these two sets would be 3 and 6. So as you can see, we just applied the Morgan's law. Now we're going to check the distributive law by finding A intersection of B union C. This should be the same as A intersection B union A intersection C. Let's first do this one on the left. We got A intersection with B union C. For B union C, we got 1, 2, 4, 5, 6. We got A, we got 1 and 2, intersection with this new set, which it will give us the following set, 1 and 2. So let's check if that applies to the right side. A intersection B, we already have that, so A intersection B is 2. Union with A intersection C. A intersection C is only the number 1. So as you can see, we just checked that the distributive law works. Now, let's talk about cardinality. When we talk about cardinality, it is basically the size of the set. Cardinality is denoted by the following notation. When measuring the size of the sets, we'll have two different groups, finite sets and infinite sets. So let's take a look at finite. Okay, so we're looking at finite sets. Let's consider set A equal to the numbers 2, 4, 6, 8, and 10. If A has only a finite number of elements, its cardinality is simply the number of elements in A, and is represented by this, which would be 1, 2, 3, 4, 5. The cardinality of set A is 5. Before discussing infinite sets, I'd like to talk about a very useful rule, the inclusion-exclusion principle. the cardinality of the union of A and B is going to be the cardinality of the set A plus the cardinality of the set B minus the cardinality of the intersection. Why do we do this? We make sure that we're not double counting elements by subtracting the intersection of these two. If we have more sets, it will be like this. A union B union C, the cardinality would be equal. The cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinality of A intersection B minus the cardinality of A intersection C minus the cardinality of B intersection C plus the cardinality of A intersection B intersection C. I know this might look a little bit confusing and think, hey, what do I do if I have 4 sets, 5 sets? So I'm just going to give the general formula. The formula to find the cardinality of the union of I equal to 1 to n for the set AI is going to be equal to the sum of I equals 1 to n of the cardinality of AI minus the sum of I less than j of the cardinality of AI intersection to aj plus the sum I less than j less than k of the cardinality of AI intersection aj intersection ak minus plus minus 1 raised to n plus 1 cardinality of a1 intersection, this goes on until an. So now we're going to talk about infinite sets. What if set A is an infinite set? It turns out that we need to distinguish between two different types of infinite sets. The ones that are countable and the ones that are uncountable. What does it mean that a set can be infinite but countable? Sets such as the natural numbers or the integers are countable, but bigger sets such as the real numbers are uncountable. The difference between these two types is that you can list the elements of a countable set. For example, set A is countable as A1, A2, A3, and so on. This might have an infinite number of elements, but you can still list them. For example, the natural number would be 1, 2, 3, and so on. The integers 0, 1, 2, minus 3, and so on. Sets do not necessarily need to be in order. To describe better, we have a definition for countable numbers. A is countable if the following is true. If it's an infinite set and the cardinality of A is less than infinity, or if it can be put into one-to-one correspondence with natural numbers. Just a simple guideline on how to decide whether a set is countable or not. Any subset of the natural numbers, integers, or rational numbers are countable. Another guideline of how to know if A is uncountable would be if they are in intervals. For example, A, B, A, B. Anything that is intervals will not be countable. So now we're going to do an example of cardinality. In this problem, we're in a party. We have 10 people with white shirts and 8 people with red shirts. With white shirts, it's going to be the set of the people that has white shirts. It's telling us that its cardinality is equal to 10. For the people that have red shirts, we're going to call the set R. the cardinality is going to be 8. We know that 4 people have black shoes and white shirts. So for the people with black shoes, we'll call that set B. So we know that the 4 people have black shoes and white shirts. So that's going to be an intersection because they have that in common. We know that this cardinality is equal 4. 3 people have black shoes and red shirts. So we know that the people with black shoes and red shirts, the cardinality would be equal to 3. We know that the total number of people with white or red, that's going to be union, or black shoes, union black, is equal to 21. What we're trying to find is how many people have black shoes. So we need the cardinality of black. Okay, so let's solve this. We're going to use the cardinality formula that we just explained. We have the cardinality of white union red union B. That's going to be equal to the cardinality of white plus the cardinality of R plus the cardinality of B minus white intersection with red minus white intersection with black minus red intersection with B plus the intersection of white with red with black. And we need to find the cardinality of B. So we already have most of these numbers. We know that this first number is going to be 21. It's going to be equal to the cardinality of white that we have, that is 10, plus the cardinality of red, which is 8, plus the cardinality of B, that is what we're trying to find, minus the cardinality of the intersection between white and red. But we can assume that if you're wearing a white shirt, you cannot be wearing a red shirt. So we're going to assume that the number of people wearing a white shirt and a red shirt is going to be 0. So this will be 0. You got minus the cardinality of white intersection black. We have that right here, it would be 4. Minus the cardinality of red intersection black, which would be 3. Plus the cardinality of the intersection of white, red, and black. That we just explained, you cannot have a white and a red at the same time, so this will be 0. By doing our operations, we have 21 here, would be equal to 10 plus 8 minus 4 minus 3. That will give us 11 plus the cardinality of B, resulting that the cardinality of B would be equal to 10. I also want to show that this problem can be solved using a Venn diagram. For example, we have here the people with white shirts. We have here the people of red shirts. We're saying that they're disjoint because somebody cannot be wearing a white and a red shirt at the same time. And here in the middle, we have the people that are wearing black shoes. From this problem, we know that the number of people wearing white shirts is 10, and the number of people wearing red shirts is 8. The number of people wearing a black and a white shirt is 4, and the number of people wearing a black and a red shirt is 3. We're trying to find how many people are wearing black shoes. So we're trying to find 4 plus 3 plus 8. The problem is also telling us that the total amount of people here is 21. What we're trying to find is how many people are wearing black shoes. So we're trying to find 4 plus x plus 3. From our data, since our total number of people in the party is 21, we can say that 21 would be the people that are wearing white shirts, which is 10, plus the people wearing red shirts, which is 8, plus x. Why are we not counting the number 4 and 3? Because this 4 is taking into account when we put the number 10. Same as the number 3. This number 3 is included in this 8. So the only one that we are not including is x. That's why we added here. With this, we can find that x is equal to 3. Since what we're trying to find is 4 plus x plus 3, that would be equal to 4 plus 3 plus 3, giving an equal to 10. That is the total amount of people wearing black shoes, which is the same answer that we got earlier. We're now in the last part of this video, so before we do anything, if you're liking this video, please like it and leave a comment down below. Now, we're going to take a look at functions. In probability, we often use the concept of functions. A function is a rule that takes an input from a set that we call domain and produces an output from the result set, something we call codomain. In other words, a function maps elements from the domain set into the codomain set. We usually use x as the element in the domain, and the function value is shown as f of x. And this is the end of the video. Please don't forget to like the video, share with your classmates or that person who's having some trouble understanding probability, say theory. And if this video has helped you, please don't forget to subscribe and leave a comment down below what you thought of the video and what topic should I cover next. And remember, if it's cold, cloudy, and humid outside, you might want to bring an umbrella. Until the next one.